Statistical models such as the least squares regression equation are probabilistic. So probabilistic models, what that means is that any predictions or interpretations made as a result of the model are based on uncertainty. It's based on probability, what's probably true. So there's not absolute certainty with any of our predictions. There's going to be variability. Therefore, we do not want to imply that there is 100% certainty behind the interpretations. So when we make interpretations, which we're about to talk about, these are probabilistic. They're not absolute. That's the first point. So we're going to interpret predicted values. So when we find a predicted value, which we're going to call y hat, the predicted value of y hat has two different potential interpretations that we could use, and they're actually somewhat similar. So the first interpretation is that it could be an estimate of the mean value of the response variable for the given value of the explanatory variable. So what we're doing is we are estimating what the y value will be for a given value of x. An estimate of the value of the response variable for a particular value of the explanatory variable. So really those pretty much say the same thing. They're very similar. Interpreting slope. Now in algebra, you may remember slope equals the rise over run, the change in y over the change in x. So keep that in mind when we want to interpret the slope of a regression model. If we have a positive slope, then what that means is if the explanatory variable increases by 1 unit, then the response variable is going to increase by b sub 1 units on average. In other words, b sub 1, that's the slope. So if the explanatory variable increases by 1 unit, the response variable is going to increase by the slope units on average if we have a positive slope. But if we have a negative slope, if the explanatory variable increases by 1 unit, then the response variable decreases by the absolute value of b sub 1 units. So instead of saying increases by a negative amount, we're going to say decreases, and then we'll take off the negative by using the absolute value. And that's, again, what's happening on average. Interpretations of the y-intercept. Now, as a general rule, the y-intercept is the value of y when x equals 0. So the y-intercept is the value of the response variable when the value of the explanatory variable is 0. However, sometimes it is not appropriate to give an interpretation of the y-intercept. So to interpret the y-intercept, we must first ask two questions. The first question, is 0 a reasonable value for the explanatory variable? So is 0 feasible? Is that a reasonable value? For example, if I'm talking about like swinging the golf club, it wouldn't make sense for the speed of the golf club to be 0 in that situation. If the speed of the golf club is 0, well then obviously the ball's not going to go anywhere. The second question is, do any observations near x equals 0 exist in the data set? So if there are no data values that are close to where x would equal 0, then we're generally not going to be able to use an interpretation of the y-intercept. So if the answer to either of these questions is no, we do not interpret the y-intercept. Otherwise, the y-intercept is the value of the response variable when the value of the explanatory variable is 0. So we'll look at an example of that in just a second. And then we have a caution. Do not use the regression model. I have a typo there. I left the L off of model. Do not use the regression model to make predictions outside the scope of the model. That is, do not use the regression model to make predictions for values of the explanatory variable that are much larger or much smaller than those observed. So for example, this right here is the golf data, again, that's graphed. And there we determined that we do have a linear relationship. And so this line might be that linear relationship. But our data only goes up to where the speed of the club is swung at 105 miles per hour. So I know I have a linear relationship between here and here. I don't know if that linear relationship is going to continue past the data that I'm observing. So therefore, it wouldn't make sense for me to make predictions way over here. What if I swing the club 120 miles per hour? Where would the ball go? Well, that's way far away from our data. So I don't know if I'm continuing a linear relationship over there at 120 or not. So again, that's the point. Don't make predictions outside of the scope of your data. You could make it maybe at like 106, which is technically outside of our data, but that's pretty close to the 105. Our data started at 99, so we can maybe do 98 or something relatively close. And definitely we can do anything in between 99 and 105, but we wouldn't want to predict outside. That kind of thing is done all the time. It's called extrapolation. And so extrapolations are made all the time, but they are very, very risky. We don't know the validity of that. So back to this example. At the end of section 4.1, we looked at the American black bear data that I have right here. And I told you I was going to continue this problem through this chapter. So we want to find the least squares regression line, treating total length as the explanatory variable and weight as the response variable. So again, this is the x, this is the y. We want to interpret the slope and y-intercept if possible. We'll always be able to interpret the slope. We may or may not be able to interpret the y-intercept. So again, ask yourself those two questions. Is it reasonable for the explanatory variable to equal 0? Do we have any data values close to where x equals 0? And if either one of those no, it's not appropriate. C, suppose a 149 centimeter bear is captured in the field. Use the least squares regression line to predict the weight of the bear. And D, what is the residual of the 149 centimeter bear that we find in part C? Is this bear's weight above or below average for a bear of this length? So I can do this two ways. Well, I guess three ways. I could do it by hand, which I'm not going to. I'm instead going to use the calculator or StatCrunch. So again, I'll show you really quickly on the calculator. If I go to Stat and Edit, I have the weight of the bears in list 1 and list 2. So if I go to Stat and Calc and Linear Regression, my x's are in list 1, my y's are in list 2. If I calculate that, the least squares regression line is given right here. So we had already found the correlation coefficient earlier, 0.7039 is right there. And so again, the slope in this case is going to be approximately 1.69417 if I round to 5 places. The y-intercept, negative 142.47092 if I round to 5 places. So my answer to part A, y hat equals 1.69417 times x minus 142.47092. I also want to show you StatCrunch real quick. StatCrunch is honestly what I would generally use more because I don't have to type the data in with StatCrunch. So here we had the correlation coefficient. Here we had the scatter plot from before. I could close those or I can leave them open. I'm going to leave them open. To find the least squares regression line in StatCrunch, you're going to go to Stat. And normally we have gone to Summary Stat, but this time we're not going there. We're going down to Regression, which should make sense because we're finding the least squares regression line. When I point at regression, I have several options over here. I have simple linear, polynomial, multiple linear, and logistic. We're doing simple linear. Simple linear means it's just a line with two variables, x and y. So we're doing simple linear, so I'm going to select that. When I do that, I get this window. All I have to tell StatCrunch is where's the X variable, which column, and where's the Y variable, which column. The X variable is this column called total length, and the Y variable is the weights. None of this other stuff matters to us, so all I have to do is say compute. When I do that, I get all of this information right here. So I want you to notice this box right here, this table. It says slope, and look right there, the estimated slope, 1.694168, which is exactly what we got on the calculator, and the estimate for the intercept, negative 142.47092, which is exactly what we got on the calculator as well. So we're getting the slope here and the intercept here. You might also notice that this is up here. Notice what's up here. So it says the dependent variable is the weight. The dependent variable, that's the Y. The independent variable, that's the total length, that's the X. And then right here where I've highlighted in blue, StatCrunch actually writes the regression equation like an equation, but they use the name of the columns as the variable. So they're saying the Y, which is weight kilograms, so that's Y equals negative 142.47092 plus 1.694168 times the total length. Total length, that's the name of this column, which is the X variable. One thing that I do want to point out, it's a common mistake. I'm going to write down that equation. I'm going to use Y and X instead of weight and length. I'm going to write that down like it's written here. And then I'll show you my screen. So notice this is the way that StatCrunch writes this equation. It writes it as negative 142.47092 plus 1.694168 times the X variable. Now, look how we write it here. Normally, we write the slope times X, and then we have the intercept. In statistics, often that's done backwards. It's the intercept first, then the slope times the X. That's very common in statistics. So just be mindful. If you look at the equation this way, 1.694168, that's the slope, right? This is the slope. And if you look at the negative 142.47092, that is the y-intercept. Now, I mention this for mainly this reason right here. In MyMathLab, when you're doing your homework, like if this was a problem in MyMathLab, they're going to ask you to write the regression equation, and lots of times they're going to do it this way. They're going to say y equals box times x plus box. So you have to fill in the slope and you have to fill in the y-intercept. Well, guess what people do a lot? They put this number in the slope and they put this number in the intercept, which is wrong. So if MyMathLab looks like this and you got this off of StatCrunch, make sure you're paying attention that this is the slope, this goes here, this is the y-intercept, this goes here. Now part B, we want to interpret the slope and the y-intercept if appropriate. So if we interpret the slope, so again, we talked about that on this previous page here. We're interpreting the slope. So in this particular case, we have a positive slope. So for every 1 unit increase in x, y is going to increase by 1.69417 units. So I like to think of it this way. Slope is equal to the change in y over the change in x. In this case, y is the weights and x is the length. So we're looking at the change in weight over the change in length. Now we have our weight in kilograms and we have our length in centimeters. So in this particular case, our slope is 1.69417 kilograms and think of that as over 1 centimeter. So if the bear's length increases by 1 centimeter, the weight is going to increase by 1.69417 kilograms on average. That's my interpretation. If an American black bear's weight increases by 1 centimeter, then the weight, I said weight right there, I mean length. If the bear's length increases by 1 centimeter, then the weight will increase by 1.69417 kilograms on average. So for every time a bear gets a centimeter longer, the weight of that bear is going to go up on average by about 1.69 kilograms. For the y-intercept, now again, I have to ask myself two questions. First thing, is it appropriate to interpret the y-intercept? Well, we had two things. One, is it appropriate for the x variable to equal 0? Well, in this case, if the x variable's 0, that would mean the bear would be 0 centimeters long, which doesn't make any sense. You can't have a bear that's 0 centimeters long. So it would not be appropriate to interpret this y-intercept. The other thing is none of our x values are anywhere close to 0. So we would be extrapolating if we were to substitute 0 into this equation. So for that reason also, it's not appropriate to interpret. So I'm going to say not appropriate. Now, many times it will be appropriate to interpret the y-intercept. So just for the sake of it, in this particular case, again, think about what y-intercept means. Y-intercept is the value of y when x equals 0. So if x is 0, y would equal negative 142.47092. So if we did have a bear that was 0 centimeters long, which of course doesn't make any sense, then that bear would weigh negative 142.47092 kilograms, which also doesn't make sense. You can't have a negative weight. But that would be the interpretation if it was appropriate. Part C. Suppose a 149 centimeter bear is captured in the field. Use the least squares regression line to predict the weight of the bear. So if x is 149, we want to find the predicted y value. Okay, so y hat would equal, use this or this, either one, y hat would equal 1.69417 times 149 minus 142.47092. So if I punch that in my calculator, 1.69417 times 149 minus 142.47092, that is about, I'm going to just round that to a whole number, that's about 110 kilograms. So I would predict that this 149 centimeter bear would weigh 110 kilograms. D. What is the residual of the 149 centimeter bear? Now this means if I look in the data, I have a 149 centimeter bear right here. And in the data, that bear weighed 85 kilograms. So what is the residual for this bear? Well, the residual is going to be the observed y value minus the predicted y value. So that would be 85 kilograms minus 110 kilograms. And if you take 85 minus 110, that is negative 25 kilograms. That is the residual. Now, is the bear's weight above or below average for a bear of this length? To answer that, I want to pull back in this interpretation right here of predicted values. The predicted value of y, which is y hat, has two interpretations. It is an estimate of the mean value of the response variable for a given value of the explanatory variable, or it is an estimate of the value of the response variable for the particular value of the explanatory variable. Now, the difference here is here we're talking about mean, and here we're talking about an individual. So on average, so what that means is this. This is the golf data again. When I substitute a particular value in the regression equation, I get the value of y that would be on the line. So that line is representing an average for different values of x. So if x is 99, then the average y value would be on that line. If x is 100, the average y value would be on that line. So that would be the average y value, and so on and so on and so on. So if x is this value, the average y value would be on the line. So that line is what we would expect on average for the varying values of x. I wouldn't expect, for example, a bear that is 139 centimeters long to weigh the same amount as a bear that is 149 centimeters long. So these predicted y values are what we would expect to happen on average for the different values of x. So I would have expected a 149 centimeter bear to weigh 110 kilograms. This bear right here was 149 centimeters, and it only weighed 85. I would have expected, based on my regression line, for it to weigh 110, but it only weighed 85. So this bear was below what I expected. It's below average for 149 centimeter long bears. So is this bear's weight above or below average? It is below average. Now again, I'm talking about this specific bear in our data. This bear weighed less than we expected, quite a bit less. As a general rule, if your residual's negative, then that value of y is below average. If the residual's positive, then that value of y would be above average.